When you send an email or stream a video, your data moves across the globe at nearly the speed of light. But to get there, it has to survive a brutal gauntlet of physical environments, pulsing through glass fiber optics and broadcasting out into the open air as radio waves. The software that guides this data, Layer 3 IP protocols, provides a perfect end-to-end map for the journey. But IP knows absolutely nothing about the physical realities of the copper cables or wireless frequencies it travels over. This diagram outlines the OSI data link layer, Layer 2. As you can see at the top, it acts as the sole translator, responsible for preparing that network data for the physical network. It has 4 primary jobs. It enables media access, it encapsulates the IP packets, it controls how frames are exchanged on the media, and it detects errors, rejecting any corrupted data. Because the physical environment changes constantly, Layer 2 protocols operate strictly on a local level. An IP packet travels from your computer all the way to a distant server, but the Layer 2 frame carrying it never crosses a router. To understand how a network actually functions, you have to realize that the data's protective vehicle is continuously destroyed and rebuilt at every single hop to survive the specific physical link ahead of it. This creates an architectural problem. How does a single network layer connect abstract IP software to dozens of radically different hardware types, ranging from Ethernet cables to Wi-Fi antennas? IEEE 802 standards split the data link layer into 2 sublayers. The upper logical link control, LLC, acts as a software bridge to Layer 3 protocols. The lower media access control, MAC, is the hardware bridge, encapsulating data for specific physical media. This split architecture makes networking highly modular. The same IP packet can travel over a fiber optic cable or a wireless network, because the LLC keeps the software interface stable while the MAC adapts to whatever hardware is plugged in. Before transmitting data onto the wire, the MAC sublayer must wrap that Layer 3 packet into a temporary protective structure. We call this a frame. Every frame begins with a header, holding source and destination physical addresses for the local link. Next is the data payload, the untouched Layer 3 IP packet. Finally, the trailer contains the frame check sequence, FCS, a checksum to detect physical corruption on the wire. It is important to distinguish these Layer 2 physical MAC addresses from Layer 3 IP addresses. MAC addresses do not indicate what network a device is on. They are only useful for finding devices on the exact same shared local network. This 3-part structure, header, data, and trailer, forms the essential protective shell that gets your data safely across one specific physical link. The exact rules the MAC sublayer uses to control that frame depend entirely on the physical topology of the network. Look at the physical topology box on the left. In a standard multi-access local area network, or LAN, multiple devices are wired into the same central location and have to share the physical media. In wireless LANs, or legacy hubs, shown here in the lower left panel, communication often occurs in half-duplex mode. Devices can both transmit and receive, but they cannot do both at the same time. This creates a contention problem. If 2 devices attempt to transmit simultaneously on this shared medium, their physical signals collide and the data is completely corrupted. The MAC sublayer solves this in wired hub networks using a method called CSMA-CD. Devices listen for silence before transmitting. If they detect a collision, they discard the corrupted data, wait a random amount of time, and resend. Wireless networks adapts this with CSMA-CA. Since wireless devices struggle to detect collisions directly, they announce the time duration they need to transmit in advance, avoiding collisions before they even happen. Contrast this with modern switches, seen in the lower right panel. These connections operate in full duplex mode, providing simultaneous 2-way transmission and bypassing contention rules completely. But what happens when we leave the local office and look at a long-distance WAN link connecting 2 distant routers? This diagram illustrates a point-to-point WAN topology, a permanent link directly connecting exactly 2 nodes. With only 2 nodes, WAN protocols like PPP are vastly simpler. There is no sharing, no collisions to detect, and no need to filter frames by destination address. Media access rules are never one-size-fits-all. The MAC sublayer heavily customizes them to survive the specific physics and layout of the immediate topology. Let's trace our data as it finally leaves the local LAN and arrives at its first major network boundary, the router. Step 1. The router receives the incoming frame from the LAN and accepts it into its physical interface. Step 2 is de-encapsulation. The router completely strips away the Ethernet header and trailer, discarding them entirely. Step 3. The router reads the bare IP packet's Layer 3 address to determine the next path. In this case, the destination lies across a point-to-point serial WAN. Step 4 is re-encapsulation. The router wraps the IP packet in a brand new, differently formatted frame suited for the serial WAN before forwarding it out the next interface. This is the cardinal rule of network architecture. The IP packet survives the entire journey, but the Layer 2 frame dies at every single hop. Because MAC addresses only represent a local physical presence, they are completely useless beyond their immediate subnet. The router must regenerate new physical addresses for every new link. Layer 3 routing decides where the data is ultimately going, but Layer 2 engineering dictates exactly how it survives the physics of getting there, one hop at a time.